So students, in the previous videos we have seen what can be the value of force acting between two charges if the charges are point charge. But in this video we are going to discuss about the value of the force if a charge is distributed over a surface or distributed over a surface area or distributed over a volume continuously. So this is the case of the continuous distribution of charge. Here you can see a charge given to a conductor is distributed uniformly. So suppose a small section of the charge is dq. So what can be the value of force acting between this charge dq and charge q naught? So position vector of charge q naught is vector r. This is position vector. So what can be the value of force acting on q naught? So force due to a small value of the charge dq, suppose given by vector df is equal to 1 by 4 pi epsilon naught. If the medium between two charges is air, this is the constant. Charge q naught is a point charge. Charge dq is a small part of the distributed charge divided by r square, vector r cap. R cap is direction of the force acting on the point charge. Certainly both the charges are positive. The direction of this force is going to be in this direction due to repulsion. Now to find what can be the value of force acting due to whole charge distributed over this conductor. For that, if we integrate or the force exerted by the different sections or different small parts of the charges can be calculated and they are added together. So for addition, we can take integration of this equation. Suppose this is equation number 1. So integration of this can be written integral df equals integral 1 by 4 pi epsilon naught q naught dq divided by r square r cap. So after integration, integral of df is force due to whole charge. F is equal to q naught by 4 pi epsilon naught is treated as a constant. So integration dq divided by r square r cap. This would be the value of force due to this continuous distribution of the charge. In this figure we can see different types of continuous charge distributions. Here in first figure, this is volume charge distribution. This is surface charge distribution and this is line charge distribution or linear charge distribution. Here in this case you can see charge is distributed over the volume of the conductor uniformly. A small section of the conductor with volume dV, suppose this section is containing charge dq. In the second case, a small section of the surface area S, that is ds, charge contained by this surface area is suppose dq. In the third case, it's a linear conductor. A small section of the conductor is of length dl and charge contained by it is dq. So in the first case, volume charge density, suppose volume charge density is given by rho. What is going to be the value of rho? The total charge dq on the small section divided by its surface area dv. So what is going to be the value of dq? dq is equal to rho multiplied by dv. So if we know the value of volume charge density, rho is volume charge density, and in the second case dq is going to be sigma into ds. This is rho into dv, sigma into ds. Here sigma is charge on the small section dq divided by surface area ds. So dq is equal to sigma into ds. In this case, what is the value of dq? dq is equal to, similarly we can write this value of the linear charge density. value of the linear charge density is lambda is equal to total amount of charge dq divided by length of the element. So dq in this case is going to be lambda multiplied by dA. So knowing the value of rho, sigma and lambda, volume charge density, surface charge density and linear charge density, we can calculate value of the force acting on the given point charge q naught in the presence of this type of continuous charge distributions. So what can be the value of force acting on this point charge? That would be written as F is equal to 1 by 4 pi epsilon naught q naught. Q naught is the point charge. Integral rho into dV divided by r square r cap. In the second case, value of the force is going to be 1 by 4 pi epsilon naught. Q naught is the point charge. Integral sigma ds divided by r square into r cap. In this case, value of the force F is equal to 1 by 4 pi epsilon naught q naught multiplied by integral lambda into dl divided by r square into vector r cap. So in this way, for any charge distribution or any continuous charge distribution, we can find value of the force acting on a given charge or given point charge in the presence of that charge distribution. So after electric force due to a continuous charge distribution, now we are going to find electric field at a point due to a continuous charge distribution. Again, the same case, when we are going to find electric field at a point or at a point of observation, suppose point of observation in all the three cases, for volume distribution, for surface distribution, charge distribution and for linear charge distribution. Suppose that point of observation is O, whose position vector is r with respect to the small sections of the volume, surface area and linear conductor. Here you can see value of the electric field D is equal to 1 by 4 pi epsilon naught. Here charge is to be taken as a point charge. This charge is no more remaining q naught but a point charge or test charge. Test charge is unit positive charge plus 1 coulomb. So no need to write that 1 by 4 pi epsilon naught dq divided by r square r cap. Now to find electric field due to whole charge distribution on this conductor, if we integrate this equation, integral d equals 1 by 4 pi epsilon naught integral dq by r square r cap. Integral dq, value of charge dq is going to be volume charge density rho multiplied by dv, that is a small section of the volume. So it becomes E is equal to 1 by 4 pi epsilon naught integral rho into dv divided by r square r cap. Similarly, for surface charge density, electric field after integration, we are going to get vector E is equal to 1 by 4 pi epsilon naught integral sigma into ds divided by r square r cap. For linear charge distribution, E is equal to 1 by 4 pi epsilon naught integral lambda into dl r square r cap. So in this way, we can find value of the electric field due to a continuous distribution of charge, whether the charge is distributed over a volume uniformly, over a surface area uniformly, or over a length of the conductor. Students, see, this is an example of the electric field due to a continuous distribution of charge. This is a linear charge distribution. Consider an infinitely long conductor placed along x-axis. This is positive x-axis, negative x-axis. Now charge given to the conductor is distributed over its length uniformly. Suppose charge on the small section of the conductor of length dx is dq. So what is the linear charge density of this conductor? Lambda is equal to dq divided by dx. And we have to find what can be the value of electric field at point P, distance of point P or perpendicular distance of point P from the conductor is y. There is a small element of this conductor whose length is dx. Suppose charge on this element of the conductor is dq. So first of all, we have to find what is the electric field at point P due to this small section of the conductor. So this electric field is suppose D. D is equal to 1 by 4 pi epsilon naught. If this conductor is in air, 1 by 4 pi epsilon naught charge on the element of the conductor dq divided by r square vector r cap. R cap is indicating direction of the electric field. Or this can be written 1 by 4 pi epsilon naught lambda dx. Lambda dx is value of the charge on conductor dx divided by y square plus x square. This is distance between point and the small element of the conductor of length dx. That can be obtained by Pythagoras theorem. This distance is suppose r. So r square is equal to y square plus x square. Now electric field at point P is in the direction D. It's a repulsive electric field. Charge on conductor dx will repel the test charge placed at point P, that is unit positive charge. Now D as being a vector, if we resolve this electric field in vertical component, that going to be E dy along y axis, along horizontal direction dex along x axis. But you can see direction of this dex component of the electric field is towards negative x axis, that is minus de sin theta, as theta is angle between r and the line joining conductor to the point T. D sin theta. What is component along y axis? dey is equal to de cos theta. So what going to be the net electric field at this point? Here you can see, if there is a small element of length dx at right side of this line, there going to be a similar element at the left side, and its electric field is again in this direction, that is d. So horizontal component of the two electric fields, that is dex, cancel out from both sides, but electric field along vertical direction going to remain same. So electric field along vertical due to all the such elements of length dx add up together. So total electric field at point P can be written as E is equal to integral dey, sum of the components along y axis. So integral, here value of x is minus infinity, as this conductor is infinitely long. So to the left of point O, length of the conductor is minus infinity, to the right plus infinity. So integral x is equal to minus infinity to plus infinity d into cos theta, that going to be the total electric field at point P. Now for two sides of the conductor, if the similar elements are there, if we add up together, then we need to multiply it by 2. So this 2 is multiplied due to electric field at point P due to elements at two sides of the conductor. So this cancel out to integral. Now value of x ranging from 0 to infinity at one side, as we have already multiplied by 2. So we are considering electric field of both sides of the conductor. Lambda dx divided by y square plus x square into cos theta, this is the value. Or this electric field can be written E is equal to lambda as being constant, lambda by 2 pi epsilon naught. Now 2 pi epsilon naught is remaining, integral x equals 0 to x equals infinity. So what is the value of x? in this triangle, this is x, y, this angle is theta. So x can be written as y tan theta. If we differentiate this equation with respect to theta, dx by d theta is going to be y sec square theta. Therefore value of dx is y sec square theta d theta. Now putting these values of x and dx in the previous equation, we can get expression for the electric field at point P. E is equal to lambda divided by 2 pi epsilon naught integral 0 to pi by 2 by 0 to pi by 2. Now all the values are in terms of angle made by R with the line joining conductor to the point. If this element dx is lying here at O, theta is going to be 0. That would be the minimum value of the angle. If the conductor is infinitely long, what can be the maximum value of theta? If point P is very close to the conductor, theta tending to 90 degree. So limit of integration is taken to be 0 to pi by 2 cos theta y sec square theta d theta. From here y square is taken common. So y square 1 plus tan square theta, that is value of x square. Now lambda by 2 pi epsilon naught sec square theta 1 plus tan square theta cancel out, y is cancelled, lambda by 2 pi epsilon naught into y integral 0 to pi by 2 cos theta into d theta. Now electric field at point P is equal to lambda by 2 pi epsilon naught into y. Integration of cos theta is sin theta. After putting the value of limit, it becomes electric field at point P lambda divided by 2 pi epsilon naught into y sin pi by 2 upper limit minus sin 0, that is 0 lower limit, and expression for the electric field at point P due to this continuous distribution of charge is lambda divided by 2 pi epsilon naught into y. Therefore this electric field, you can see lambda divided by 2 pi epsilon naught y. So electric field due to this continuous distribution of charge at point P is inversely proportional to y. As distance of the point increases from center of the conductor, the electric field decreases. At the same time, electric field is directly proportional to linear charge density of the conductor. If more and more charges are present per unit length of the conductor, electric field at point P is going to be stronger. So students, see another example of electric field due to a continuous distribution of charge. In this example, electric charge is distributed uniformly over a thin uniform ring. Charge given to the ring is uniformly distributed over its length. Suppose positive charge is given to the ring. So what is the linear charge density of this ring? Linear charge density of the ring is lambda equals charge given, that is dq divided by 2 pi a. Or if charge given to the ring is q, then q divided by 2 pi a. So what is the value of charge on the small element of the ring, that is of length dl? So amount of charge on the dl length of the ring is suppose dq. So value of dq is q divided by 2 pi a, that is linear charge density of the ring multiplied by length of the element. So there are two diametrically opposite elements of length dl are there. First element, second element. So electric field at point P, suppose point P is here. Point P is lying on the axis of the ring. Axis of the ring is a line passing from the center of the ring perpendicular to its plane. Plane of the ring is perpendicular to the plane of this board. Ring is placed like this, suppose. This is its diameter. Now at point P, distance of point P from the center of the ring is x. The radius of the ring is a. So distance of point P from element of length dl is suppose r. By Pythagoras theorem, the value of r square is equal to x square plus a square. So similarly, this distance is again r square is equal to x square plus a square. So electric field at point P due to element of length dl is in the direction d. Similarly, electric field due to this element diametrically opposite is d in this direction. As both the electric fields are repulsive, if we assume the presence of a test charge at point P, the force due to this positive charge on the ring is going to be repulsive. Now this angle is theta, so as this angle is theta, now what is the value of components of the electric field? Horizontal component of vector d is, if this angle is theta, this angle, and vertically opposite angle theta, so horizontal component of d is d cos theta for this electric field, and again d cos theta for this electric field. But what about vertical components? Vertical component of both the electric fields, d sin theta and d sin theta, they are equal and opposite in direction. So these two components cancel out and there is no contribution of this component to the electric field at point P. But total electric field at point P is going to be sum of the horizontal components, that is d cos theta and d cos theta. So if we divide this whole ring in such diametrically opposite elements, there are so many elements whose electric field and their horizontal component is going to be in the same direction. They add it together. For the addition, if we use integration, so total electric field at point P due to presence of charge on the length of the ring can be written as E is equal to integral 0 to 2 pi a. The maximum length of this ring can be 2 pi a if a is its diameter. So E is going to be equal to integral 0 to 2 pi a kq, k is electrostatic constant, divided by 2 pi a dl divided by r square. Value of dq is, this is kq dl by 2 pi a into r square. So E is equal to kqx divided by 2 pi a 1 by r cube, r square into r, 1 by r cube integral dl. Certainly this integration is going to be again with the limit 0 to 2 pi a. After integration, this quantity is constant, kq into x. Component cos theta is also there. What is the value of cos theta? Cos theta is x by r. So here remains E is equal to kqx by 2 pi a